So I want to welcome you all to IAA's inaugural event. IAA, as you all know, really spun up largely during COVID. So we've been around actually for several years at this point. But this is our first time to actually get together with folks in person on campus and to talk about the research that people have been doing in the program. Of course, yesterday we had our big event across at the Steve building. So today we have a couple of great talks kicking us off. So Ralph Semmel, the director of the Applied Physics Lab, will be getting us going, followed by Bobby Braun, who's going to talk to us about challenges for autonomy in space. So I'm very much looking forward to what Bobby has to say. Of course, he joined us here in the Baltimore area. Is it sort of in the last year or so? It came to us from the West Coast, came to us from the Jet Propulsion Lab out in the Pasadena area, if you don't know where JPL is. So Bobby has a long history in working in the space world and managing large projects and large organizations. We'll have a little break, and then we're going to hear from our seed project PIs, and a few of the IAA projects which have spun up in addition to the seed projects in the sort of 1:15 to 3:30. So it's going to be really fast talks. They're not long talks, kind of scene setting, if you will, for the reception where we'll have a set of posters around and you'll be able to wander around, meet the folks doing the work and chat with them. The other thing that we'll be doing, though, is right at the end of this discussion of the projects is I'll be describing our call for proposals for the next round. So the seed project money used a good chunk of the president's investment to get IAA up and running. We have another round coming, and it really is shaped by the feedback that we've gotten from the PIs, both at APL and at Johns Hopkins. And I'll talk a little bit also about how that'll work with the flagship projects. So just by background, you all know that we are a joint venture of the Whiting School and the Applied Physics Lab. And so one of the things that we have been investing heavily in is making it easy for you all to work across campuses. And in fact, we do have our new facility. It's at the Steve building. So here is Dean Ed, who currently is out at the Applied Physics Lab. Well, Ralph is here with us on the Homewood campus. But yesterday we were opening our facility at the Steve Silver building. And as you all probably know, if you've been following the investment, that building is going to see a lot of investment in that immediate area. So it's a little bit out on the edge of campus now. I think sort of 5-6 years from now, it's going to be very much at the center of a lot of what's going on, particularly in the test and evaluation space of a lot of our advanced technologies on campus. So I don't have to tell you all, autonomy is everywhere. There's big changes that are occurring out there in the larger world. There's sort of withdrawal in the industry side of investment on the tech side, which might be kind of a good thing because it's sort of shaking out some of the weaker players in, for example, the transportation space. And for us, it sort of begins to surface the really hard problems that we need to work on. I think we also sort of all recognize that making these autonomous systems work is the place where most of your money is spent. So kind of coming up with an AI system is an investment, but making it work is what costs you most of the money. So the seed project portfolio, which you'll be hearing about after Ralph and Bobby, consists of a set of projects which actually connect groups across the Applied Physics Lab and what I call sort of the academic campuses. And so without further ado, I'll try to get off the stage here quickly so that we have time for Ralph and Bobby. I'll just give a very brief introduction to Ralph Semmel. Ralph, I met originally, I think, through his role on the Defense Science Board, which is kind of the mother of all defense advisory agencies. At the time, I think I chaired the Naval Research Advisory Committee, which is was an old established advisory committee set up at the end of World War II. But we had a lot of sort of interaction between the various advisory boards, and I remember talking to the DSB on a number of occasions back in my, I think probably even in my Mbari days. So it might have been 10 years ago. So Ralph has been a director of APL for 12 years now, and APL, for those of you who kind of don't know how to think about it, it really takes on sort of existential problems associated with national security and the future of our nation. And it really has this big focus on transformative innovation. There's a great origin story, which is in the book 12 Seconds of Silence. I've got that right. I always add an extra second. I don't know the number of people I've sent looking for 13 seconds of silence. So, and one of the things that he's done is he has overseen a period of enormous growth of that organization. So I couldn't find the 2010 numbers, and the 2021 numbers aren't on the site there. But 11 from $1 billion to almost $2 billion in the span of 7 years, from 2013 to 2020. And he has an enormous interest in connecting with us on the academic campus, as witnessed by his being here today with us. He's a West Point graduate. He has a master's degree, including a master's degree in system engineering, and a PhD. He is actually a Johns Hopkins graduate. And he actually has also chaired some of our educational programs. So he chaired in the EP program, the program in computer science, information assurance, and I think information security is the IS there. And as he founded, actually, I think shortly after 9/11, the APL Applied Information Sciences Department, which is now quite a large department inside of APL. So he's had numerous leadership and senior advisory positions both at APL and outside of APL, and we're extremely lucky to have him here today to give us sort of his vision of how autonomy wraps into what they're doing out at Applied Physics Lab, and hopefully some ideas about how we can connect and team with that campus. And then he'll introduce Bobby. So over to you, Ralph.
Thanks, Jim. Thanks for the introduction. That was a much more extended introduction than I expected. When Bobby comes up, I'm going to say, "Here's Bobby." So I do want to say thank you for your leadership and your vision. We're very fortunate to have you as the head of the IAA, and I really want to extend my thanks to all of the entire IAA team. This really is a crucial activity for not just APL and Hopkins, but for the world more broadly. And I'd like to take a few minutes just to kind of give you a sense of where we're coming from an APL standpoint before turning it over to Bobby. And I'd like to kick it off. Let me make sure this works here. Yep. I want to kick this off by asking you to imagine a hurricane tearing through the United States, leaving wide swaths of destruction. FEMA and local agencies are standing by to deliver relief, but it's unclear where the worst damage is. So aerial images taken by aircraft and drones are entered into a system that autonomously studies them and quickly identifies the hardest hit areas and creates the best routing and course of action for first responders. So the question, would you trust an autonomous system to direct the delivery of critical resources following such a disaster? Have autonomous systems really reached that state yet? Okay. Or imagine training a computer vision system for a transportation hub that can recognize humans and their baggage passing through a subway station. But the data used to train that system was manipulated on purpose and perhaps years ago, such that by putting a certain small patch on a person would make the system identify them as, say, a teddy bear, as you see here. And this is actually work that's being done by a staff member at APL who is also a graduate student at Johns Hopkins. Okay? So how do we ensure that the data sets we use are not only free of bias, but free of malicious or manipulated elements? Okay, finally, imagine a large asteroid is discovered careening towards the Earth that has a good chance of hitting our planet in the next decade. We launch a spacecraft to intercept and divert that asteroid. But because the spacecraft ends up being tens and possibly hundreds of millions of miles away, it cannot be steered in real time by controllers on Earth. In this case, I'm not sure why this is flipping through. I think you're... So in this case, we were quite successful. But how would you feel about putting the fate of millions and perhaps billions of lives? Did you read recently about the potential killer asteroid? Just in the news yesterday or the day before, right? How would you feel about putting the fate of millions, if not billions, of lives in the virtual hands of what is basically a chunk of metal, expensive metal, okay, complicated metal, but metal with some fuel, a camera, and a set of autonomous guidance algorithms? Right? This leads us to believe it's absolutely possible, but when millions and billions of lives are at stake, are you willing to take that risk? Right? So now, as you've probably realized by now, these are not imaginary scenarios. They're the kinds of real-world challenges that we face and that we are tackling at APL, all involving autonomous systems that need to be trusted. In other words, we need assured autonomy. Now, it turns out, just dropping back in history a little bit, there we go, okay. All right, so what you see here are two robots. They're called, and they literally, these are their names. On your left is Ferdinand, and on your right is the Beast. And these were among the first robots that were ever developed, and it was back in 1960 and 1961. And they were designed to basically scavenge for power in hostile environments. They were to demonstrate how one might go about scavenging for power. And we're talking about battlefield environments, undersea, or far-off alien worlds where there wouldn't be power outlets. But the way to demonstrate back in 1960 or 61 was to have them roam the halls of APL and look for receptacles that they could then plug themselves into when they were running low on power. Well, these were not trustworthy systems, all right? And in fact, they routinely were overwhelmed by simple but cumbersome obstacles in their environments. And in particular, back in 60 and 61, engineers and scientists used to collect a lot of papers, and they would keep them stored in their rooms, and they would form piles. And the Beast would wander into a room, look for a receptacle when it was running out of juice, and basically was blocked by a pile of paper, and it ran out of power and died. And then they'd have to call the Beast administrator to come and pick up Ferdinand or the Beast and then power them up and let them off on their way. So clearly, you know, this was not what we would characterize as assured autonomy, but it demonstrated that we saw the need for something like assured autonomy even back in the early 60s. Now, more recently, we recognize we might be approaching an inflection point in AI, and that's still to be determined, right? You know, Jim just talked about kind of the, you know, dropping down, if you will, of some of the work that's going on, especially you might have read about the company for autonomous cars and so on, basically being sold off. So we're seeing, you know, some things start to play out, but I do think we may be approaching an inflection point in AI because we really are doing things that are far more realistic than they were back in the AI springs of the 1970s and the 1980s. We've gone through a number of AI springs and winters, obviously. But we created this Intelligent Systems Center to bring together machine learning, robotics, autonomous systems, and applied neuroscience. And we quickly recognized the significance and importance of assurance when working on these systems, and we partnered with the Whiting School to create the university initiative that we call IAA, the Institute for Assured Autonomy. And we saw the need and the opportunity to create what amounted to a national center of excellence to tackle a big challenge, namely making sure that complex systems, which have become essential to life today as we know it, could be trusted in all aspects of society. Now, the Institute for Assured Autonomy is a large collaborative effort between APL, the Whiting School, and involves some of the other divisions as well. And from an APL standpoint, we're seeking to move autonomy from fundamental research to applied research to actual operational use. And we're particularly pleased to be able to work with the Whiting School of Engineering researchers on the many challenges that accompany transitioning capabilities like we're talking about here today. Now, as we develop increasingly powerful autonomous systems at APL, we've come to realize just how difficult it is to ensure that a system behaves appropriately. How does the system make decisions? Think about systems where lives are at stake, right? How does the system make decisions? How do we validate performance, especially if decisions are not guaranteed to be repeatable? Is the system free of bias? Is the system secure? And let me give you a deeper sense, if you will, of what we're talking about at APL. So in 2020, and we're still involved in this program, APL played a key leadership role in DARPA's Alpha Dogfight program. Everybody know what DARPA is? DARPA, Defense Advanced Research Projects Agency. Okay. We ran what amounted to an esports competition, and this was actually pretty cool, and you could find it on YouTube. The esports competition was actually supposed to be run out in Las Vegas. Okay, that's how open it was going to be, but because of the pandemic, they ended up having to keep it local, and so we actually set up a big stage area and ran this esports competition at APL. 8 different teams, primarily industry, battled for 3 days to earn a chance to pit their AI, so these are 8 AIs, against a human F-16 pilot in a virtual air combat simulator. So think about, you're fighting in a virtual space, and you have 8 AIs that are competing against one another. And so then you go to 4, you go to 2, and you end up with a winner that is the AI that dominated the event. APL played a critical role developing adversary AIs for training, because you need lots of training data and so on, creating the simulation environment and coordinating and communicating the entire competition event. At the end, that AI that won went against the human pilot in 5 dogfights. You want to guess what the score was? AI, it was 5-0. AI 5, human 0. Okay? While there's much yet to be done, to make Alpha Dogfight a reality, the results are somewhat indicative of the inflection point that I was alluding to earlier. So now, suppose that a human pilot in one aircraft is asked to fly side by side with an autonomous air vehicle that's piloted by the AI. Can the human pilot trust that potentially lethal autonomous air vehicle? And what happens when we reach a point at which the human no longer makes sense in the system, when the human pilot might be a hindrance rather than essential to the system? How will we recognize when we've reached that point? And when we have reached it, will we really trust the autonomous system to act without supervision, especially when lives may be at risk or at stake? Okay. These are tough autonomy questions, and there's clearly an ethical aspect to some of those questions. And you might say, well, always have a human in the loop. But it's not always the case that a potential adversary would choose to have a human in the loop, which would give the adversary a distinct advantage in a situation where we would choose to have a human in the loop. What do we do? There's not a definitive answer to this kind of thing, but it's a kind of technical and ethical question that we have to grapple with. Now, of course, while we do a lot of defense work at APL, it's not just about defense. We do a lot of non-defense work at APL. And there are many other applications that we're exploring, including in healthcare, cybersecurity, and even climate change that lend themselves to autonomous systems. And so with just that thought in mind, we created a national health mission area several years ago and have been applying AI and autonomy technologies to areas such as precision medicine. For example, automated monitoring systems can spot health crises trigger conditions much faster than humans can, but we must make sure they're designed correctly and respond predictably. And we must, and I've mentioned this already, we must ensure that the systems are not inappropriately biased, which you probably have read about. Bias is a significant issue in health systems today because of the data that we draw from for learning. So to ensure this, we're focused on an IAA project now that can increase reliability of AI systems while simultaneously decreasing bias. Now, what about cybersecurity? So this is something called the Live Lab that we have down at APL. If you come down to APL sometime, we'll take you around and give you some demonstrations down in the Live Lab for folks that haven't seen it. But cybersecurity is also an area where autonomous systems are useful when real-time response exceeds human capability. And think in this case response to botnets, distributed denial of service attacks, and so on. Now, when a malicious actor unleashes a cyber attack, the best defense must often come from an equally fast automated system. At APL, we design and develop a number of these kinds of autonomous systems to protect networks. And just to give you one example, we developed a technology called Mosaics. We actually created this in conjunction with a number of national laboratories. And this enables autonomous monitoring of facilities ranging from government installations to power and water plants. And in tested environments, it's had a 100% success rate identifying attacks with less than a 1% positive false alarm rate. So very promising technology. Now recently, and this one may sound a little odd to you, but recently, APL's also started exploring how to develop solutions to climate change, and in particular, rely on autonomy as a basis for some of that work. And let me give you just one example. We're part of something called Climate Trace, the Climate Trace Coalition. This is associated with Al Gore, if you're familiar with that activity. And it aims to estimate global greenhouse gas emissions. What we're trying to do is estimate global greenhouse gas emissions using satellite imagery and other sources of data, often in locations where getting ground truth information is not possible, right? And so last year, an APL team proved for the first time that AI, machine learning, and remote sensing could be used to accurately estimate road transport emissions just from satellite imagery. Now, when you think about this from a climate standpoint, it's critical, especially in today's highly polarized environment. It's critical that these estimates be rock solid, especially given the evocative nature associated with climate change and the differences of opinion that you will hear expressed in the political regime. So if we can get these things to be autonomous and really provide us with ground truth data that one cannot question easily, there'd be a tremendous advantage and an ability to respond to some of the climate challenges we see facing the nation and the world today. So what does all this mean, and what might the future hold? Well, every facet of life is likely to be touched by AI and autonomy. With IAA, we want to enable society to take advantage of the full potential that autonomy has to offer by making sure autonomous systems are effective, safe, resilient, and secure. And so I encourage this group here and the broader group associated with IAA to be bold, to think big, and we should focus on strengthening our collaborations. IAA has been a great vehicle for facilitating collaborations between APL and the Whiting School. Focus on those collaborations while further engaging the external community. And so I really am looking forward to the amazing results that I think this IAA partnership has the potential to produce. And so now, with that, let me take the opportunity to introduce our next speaker. Here's Bobby. No, just. Okay, so one of the unique conditions of spacecraft, one of the unique operating conditions of spacecraft, such as DART, the Double Asteroid Redirection Test spacecraft, is that they need to be able to take care of themselves. They need to be able to avoid hazards, monitor their health, and perform operations on their own. The head of our space exploration sector is Dr. Bobby Braun, as Jim mentioned. He's going to take you inside the world of autonomy for space operations, discuss some of the successes in this area, and look at how the future of autonomy requires collaboration and partnerships, such as we can have here with IAA. So Bobby joined APL earlier this year. He's had a big splash already with things like DART. He joined from the Jet Propulsion Laboratory, where he served as the director for planetary science and was also the Bren Professor of Aerospace at Caltech. And earlier in his career, Bobby has a long history with academia. He was a faculty member at Georgia Tech. He was the dean of the College of Engineering at the University of Colorado Boulder, and he was also NASA's chief technologist. So he's had broad academic, government, and industry experience. He's a member of the National Academy of Engineering, and in his spare time, he's even managed to write a few hundred papers and found a company. So I know you're going to find this talk fascinating. Thank you, and over to Bobby.
Good afternoon. It's great to be here with you all. I really, Jim, thank you so much for the invitation to be part of this. I'm thrilled to be part of the Hopkins ecosystem, and as Ralph said, APL looks forward to additional collaborations with Hopkins and with IAA in this domain. I'm really happy to be here with you today and get to talk about really the one love of my professional career, which has been spaceflight. I've been working in robotic space systems for about 30 years now. And, when I first started thinking about this talk and spaceflight, I was like, well, of course they want to know about space systems because, we're rocket scientists and, we're cutting edge and all those things that you think about with space. But when it comes to autonomy, for most of our deep space systems, we're still in the early part of the game. We're still in the early stages. And that's really what I wanted to talk to you about today, and also talk about some of the examples where we've just broken through with some, for spaceflight at least, advances in autonomy. So as you know, the early days of spaceflight were built, whether it was human systems or robotic systems, were all built on ground-in-the-loop operations. Right? Houston, we've got a problem. Right? What does that signify? It signifies that they're calling back to mission control and saying, help, what do we do? All the brains, if you will, are on the earth in Houston in that statement. And the same was true in our robotic systems, particularly for the larger, more expensive systems, the systems that we fly rarely, like once a decade. If the price of your spacecraft is on the order of thousands of people, you're going to make sure that those people are involved in the operations. And so the early days of spacecraft was very much a human-in-the-loop centric approach, and that mindset has really persisted through our systems even to today. However, in the past decade, there's been some really remarkable examples where autonomy was required and where autonomy was performed in a way where people are, spacecraft designers now are thinking about their systems differently. And I'm going to walk you through those examples and then posit what that might mean for the next decade. Now, as when Ralph was giving his talk, by the way, the question that was in my mind was, do I trust this PC for a presentation that I made on a Mac? I can answer that. Yeah, and do I really want to use this clicker, right? Those were the questions that were in my mind. But in reality, if we're going to be using autonomous systems on deep space, one-of-a-kind science spacecraft, or on spacecraft that are carrying humans to the planets, there are a number of things that we're going to have to do differently. We're going to have to change our approaches to verification and validation. We're going to have to come up with trust and assurance testing programs well before launch, and those kinds of things really are not well developed for spaceflight today. And then we're going to have to continue to improve the onboard fault management activities, and the computing resources that allow those autonomous systems to flourish. That's something also that doesn't typically happen in spaceflight, right? The computers that we fly in space tend to be less powerful than those in your iPhone, just as an example. Now, while I'm talking about some of the challenges, I do believe this is the future, and what I'm going to show you today points to my belief that there's no turning back, and that autonomous systems are going to enable a whole new class of planetary and spaceflight exploration. Now, just so we're all on the same page, I wanted to define what I mean by autonomy and autonomous systems, because people have slightly different definitions. Now, if we're talking about the world of robotic spacecraft, satellites about the Earth, or spacecraft at Mars, or what have you, you know that these are automated devices, right? There's no question about that. And by automated, I mean the control of the spacecraft or the system is done by mechanical or electrical means, and that means takes the place of having a human on the spacecraft, okay? However, what I'm trying to get across to you is that for most of spaceflight history, these robotic emissaries have still been controlled by humans here on the Earth. They're not self-directed. They're executing a set of pre-planned instructions. Maybe their instructions get updated on some regular cadence, but even those instructional updates are planned by us in advance. Whereas what I mean by autonomy is the ability of these same systems to achieve goals operating independent of us back on the Earth. That requires the ability for self-directedness and self-sufficiency. And there have been some notable examples of this in just the last few years. On this slide here, I'm showing two very well-known set of spacecraft. In the top is what's called the A-Train. It's a series of Earth-observing spacecraft that are going at a certain time in the afternoon. That's why they're called the A-Train. And they take continuous measurements over the Earth's surface at a specific time, and that allows the scientific results to be correlated over many days, months, years. But these operations are all pre-planned and pre-programmed by people on the Earth who every day tell the spacecraft what to look at and when to do it and when to send the data back in large mission control rooms, right? We also have the Curiosity rover on the bottom. The Curiosity rover was totally operated in a pre-planned way, and then once it was proven, once it accomplished its science mission, we started to use it in more of a test mode, and we developed a set of autonomous operations procedures where Curiosity, as it drives across the Mars surface now, is self-directed and is determining its own course, its own time, speed, when to stop, when to move. We basically give it high-level waypoints, and it does the rest, okay? So that's an example. When Curiosity was first on the surface, it was very much in an automated mode. But over time, we gave it more and more freedom, and now I would argue that it's operating in an autonomous mode, okay? Now, for spaceflight, there we go. Why do we do automated systems? Well, it's because we don't want to take the risk on autonomy. So you can turn that around and you can say, well, when would you do autonomy? And there are a number of reasons why autonomous systems make sense for spaceflight. Clearly, if the decision-making speed needs to be rapid, and you're out at Mars, and the one-way light time is 9 to 14 minutes, so the round-trip command is 18 to 28 minutes, there's probably a reason if there's a rover heading towards a cliff, for example, autonomous operations might make some sense. Or when that's an example of when time-critical decisions have to be made on board, right? Another example would be in deep space, it's very hard to send all the data back. It takes a lot of power and a lot of time. Our bandwidth, our telecom path is like a little pipe. It's not a big pipe, okay? And so when we have these ginormous orbiters, like the Europa Clipper orbiter that's going to go out to Europa, a moon of Jupiter, launching in 2024. It's got 12 instruments on board, and those instruments are going to be sending back a world of data. We're going to actually have to decide on board which data to send back because we can't get it all back fast enough. So we're going to have onboard processing capability so that we don't send the raw data back, but we send higher level data products produced on board. And we have to trust that that spacecraft will do that production of the data that we're most interested in and the prioritization that will do it right. So that's another example of why we're going to move over time to autonomy in spaceflight. Now, NASA actually has a roadmap that they laid out for the use of autonomous systems in space. The roadmap, I got it on the right on this slide if you're interested. It was published in the summer of last year. And it's pretty good, actually. In preparation for this talk, I went through the document. And it basically takes you in 5 different areas from the way that NASA has been doing operations traditionally, the conventional space missions on the left-hand side of this slide, to what NASA would like to go to in the future in a fully autonomous sense, and the investments that NASA is willing to make in things like control authority, spacecraft commanding, situational awareness, communications, and other capabilities to get there. If you're interested in more descriptions about kind of the roadmap process and how NASA is making investments for spaceflight and what this might mean for future systems, I'd really encourage you to take a look at this report. At APL, I can tell you that we are contributing in several of these domains, and our spacecraft are getting more autonomous as a result. So before I go much further, I wanted to show you a couple of examples. And these are things that have occurred in just the last few years in spaceflight where I kind of woke up, if you will, to what autonomy can bring. My first example is from 2021, and it's the landing of the Perseverance rover. So I'll just show you this video, and then I'll walk you through it in a little more detail.
Propulsion, go. EDL phase lead, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute has deployed, and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. Skycam maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
But I want to call your attention. It went by quick. You probably didn't notice, but Swati Mohan, who was in the video, she's the voice that you're hearing, and she was, the voice of NASA during that broadcast. And about 30 seconds, 20 seconds into the video, you heard her make a call out, which was the spacecraft is now executing to its onboard targets. It went by really quick. You might not have heard it, but it's in there. You can listen to it again later and you'll hear it. I've worked on 7 Mars landings. This was my 7th. This was the first time that nobody knew where we were going to land. The rover decided as it was hurtling towards the Mars surface, as it was falling towards a potential crash landing, it was deciding on board where to go. I've been a navigator for 3 missions, and us navigators, we always have pools, right? And we're going to make bets on where it's going to land, and the best navigator usually wins. I've won 1 time out of 3. But I literally I knew the region on Mars that we were aiming for, but where in that region we were going to land was not determined through a pre-planned sequence of events. It was not determined inertially. It was determined in the logic of the computer that was descending towards Mars based on onboard maps and conditions that it was sensing in real time. In fact, I have, on my next slide, I have a statement or an data that shows how that was actually done. But that is a remarkable thing. This is a $2.5 billion rover. There's only one of them. It is the rover that is going to be that is right now gathering samples on Mars to bring them back to Earth. So it's the future, if you will, of NASA's entire Mars program. It's something that thousands of people worked on for about 8 years, and yet none of us knew where it was going to land. It was also a lifting guided entry, so it had its own ability to steer through the atmosphere before the heat shield fell away and it could see the Mars surface. And when it could see the Mars surface, what it saw was something that looked like this, and it actually didn't look like this, but it would color code what it saw based on its onboard maps of hazards. And so if you look at the right hand in the bottom image of this slide, those are percentages, and you can see that we gave percentages of landing failure, right? So small is good, down near the bottom where it's red is bad, and we didn't want any more than 4% chance. So anything between 4 and 100% chance of failure is all death, right? We called it all the same to kind of steer the rover away from that. But after that, the rover was on its own to determine. And in fact, I don't know if I can make this work. Let's see. I can't see it. Let's see. So right here, can you see my cursor? No, you can't. The laser pointer. Is that a laser pointer? The laser pointer works? Yeah, I'm colorblind. Anyway, so how can I do this? So you see. Yeah, so trust. All right, so there's in the image on the left, in the center, there's like a low probability area that's on a 45-degree slant from the bottom left to the upper right. There's a couple little dots in it. That's where all of us on Earth thought it was going to go. We called that the landing strip. The science that we wanted to do is around those regions in the red areas that we didn't want to land in, but we wanted to explore. You can see the little dot. That's where we actually landed. The reason that we landed there is the winds were significantly different than we expected. And we were on the parachute for about 2 minutes, and it carried us to the southwest into that center of all that red stuff in there. And instead of diverting to the left, which it could have done, it was actually a higher probability if it diverted to the right and landed in this little safe zone, if you look at the right image, where the dot also is. Okay? Now, we did millions of simulations, and Perseverance landed in this spot, less than 1% of the time. Okay? So this was a pretty, for all of us, it was quite a surprise. In fact, Perseverance's journey across the Mars surface was modified. The whole plan was thrown out, and we developed a new plan because of where we landed, and we didn't know where we were going to land until that day. So to me, this is a great example of autonomy in space systems. It's something we hadn't done before in the Mars program. We did it in this case because the science required it. We were going to a pretty treacherous site where the science needed us to go. And this treacherous site had safe zones each about the size of a football field. surrounded by dangerous terrain that we didn't want to land in. And our inertial approaches, the approaches we'd used in the past weren't good enough to qualify for those sites. So we had to develop this technique. We did. We tested it out. We proved it out here on the Earth in ground-based testing, in drop testing, in simulation, and then we did it for the first time on Mars. So anyway, I think that's just one example. Another example that I'm going to point to, Ralph already touched on, is DART. We just executed the DART mission at the Applied Physics Laboratory. This is a close-up of the DART spacecraft showing you the imager. It's called Draco. That's in the center of this slide. The DART spacecraft was basically a 500-kilogram spacecraft with one instrument, a camera, and then computers and guidance algorithms and propulsion tanks to execute what we needed it to do. So the mission was designed to go to an asteroid and impact that asteroid, an asteroid that we can't even see from the Earth, an asteroid that we don't even know precisely where it is in its flight about the sun, right? And so for that reason, autonomy, is a requisite part of this mission. By the way, we were going to an asteroid we're going to hit an asteroid that we knew very little about. What's shown in this slide on the left is some images taken from the Very Large Telescope in Chile. You can see the asteroid streaking across the sky. And from radar observations, what we knew is that there was a primary asteroid, shown in the image on the right, for example, and we had a general idea of its shape, kind of a blob, if you will. We knew roughly the size of the blob, and we knew its trajectory in its path around the sun. But there was also a smaller asteroid that was in orbit, if you look at the right-hand image, about the larger asteroid. And what we wanted to do was hit the smaller asteroid, right? It's a much harder thing to do. We can't see it from the Earth, by the way, but we can see, I don't have it on this slide, but we knew it was there because of light detection, basically changes in the light pattern, just like detecting exoplanets around other stars. As that smaller asteroid went around the larger one, the light curve changed, and so we knew its orbital period. And that's about all we knew, okay? We didn't, for instance, know the shape of the smaller asteroid. A smaller asteroid's named Dimorphos. Is it going to be round? Is it going to be shaped like a dog bone? In one of the simulations, we had it shaped like a donut. And so the team was very surprised when they were right on course, but had no impact because they flew right through the hole. But I mean, I doubt it would have been a donut, but the shape of this asteroid that we were going to hit could have been any shape. And so once again, given the time requirements, you can see why the need for autonomy. This gives you a sense of the timeline. So on we were, of course, traveling through space for many months to go the millions of miles required to execute this rendezvous and intercept. On the day, September 26th of the impact, even a little more than an hour out, look on the left-hand side and look at what you could see, right? If you look very, very, very closely, you can see Didymos at 8 pixels and Dimorphos, the object we're going to hit, is 2 pixels. From your seats, you probably can't even see Dimorphos. But that dot in the center is Didymos because up until at that time, about just before that time, we had handed over operations from us on the ground to the onboard system. So because we knew where Didymos, the larger asteroid, was, what we were doing was targeting Didymos, right, the whole time until 4 hours out. 4 hours out, we gave control over to the onboard computer and told it that when it found the smaller asteroid, Dimorphos, and was sure that it found it because it had enough pixels, that it could deflect from tracking on the big one to tracking on the small one, all autonomously. And so this is what it looked like an hour out, 2.5 minutes out. You can see the larger asteroid in the lower right of that second image, and you can see it's clearly locked on at this point to Dimorphos because it's in the center of the image, and then as it gets closer and closer. And as Ralph showed you, This is what that looks like speeded up, the last 5.5 minutes of that in real time. So this is a 10 times real speed. As we go by the larger asteroid that we could see from Earth, and for the first time, the smaller asteroid begins to come into view, or comes into view clearly. You can see what its composition is. This was a super exciting time for all of us, and we're dead on. So after going more than 7 million kilometers around the sun, we missed by 13 meters from the centroid of an object that we couldn't see. Right? And of course, celebrations were everywhere. In our operations center, all across the lab, really all around the world. Now, how do we do that? Well, embedded within the computer and embedded within the software was something that we called SmartNav. And SmartNav is based on missile defense technology, the algorithms and the fundamentals of that tracking, retargeting, lock-on. You know, it's very much like what you might imagine in missile defense. And at APL, we actually took the missile defense designers and brought them into the space sector where they could work with the space systems engineers hand in hand to make this mission a success. The spacecraft had the ability for self-information and for making decisions. Do I do a propulsive maneuver? Do I, is something really going wrong, so we're going to abort and do a once around? It would take 2 years, by the way, to do a once around, but it was possible. And so the spacecraft had the ability for the last 4 hours to think through the entire scenario. And we, in the control room, while we looked very stressed, and we were basically observers, like everybody else in the world. This last image here comes from Alicia Cube. Alicia Cube was provided by the Italian Space Agency, and it was a CubeSat that flew along with us. And 15 days out, we dropped off, and it flew back in formation to come behind where our impactor was 15 minutes after impact. So it could observe the impact itself, the impact event itself, and that's why you see the glow that's shown in these images. It's just going back and forth, showing you the before and after of the impact. Of course, our autonomous spacecraft was destroyed, and that was the goal. But this was another huge success, in my view, for autonomy. Now, looking forward, there's going to have to be more and more such systems in spaceflight. And the next one that I want to speak about is Dragonfly. We are building the Dragonfly spacecraft at the Applied Physics Laboratory right now. It's a quadcopter, maybe like the quadcopters you have on campus, although this one's the size of a small car and is nuclear powered. But it's a quadcopter designed to fly on Titan, a moon of Saturn that is known to have the prebiotic chemistry, the building blocks of life. That's why we're going there. And Saturn is very far away. And there aren't spacecraft at Saturn waiting for us. And so this system will have to be very much self-directed and autonomous, not just in the science operations that it does, but as it lands, one time it's going to be taking images for the next flight and then processing and utilizing those images to plan the second flight, and from the second flight to plan the third flight. So yeah, the ground will be in the loop between flights, and we'll be downloading data, and we can pause the operations and things like that. But this will very much be an autonomous system. And other examples, if you think farther in time, these are missions that are just concepts today. They're not funded by NASA quite yet, but there are plans to land on Europa, a moon of Jupiter, to land on Enceladus, a moon of Saturn. These are both ocean worlds where there is a great deal of liquid water beneath the surface that we would like to understand and explore. And so if you think about landers in these extreme environments, the only way they're going to be successful is with autonomous operations. We don't have the infrastructure in these places like we do at Mars. to keep the ground in the loop. There's too many times when the Earth's not in view, so you can't wait for the Earth to come into view. You'd lose too much time. It's a very cold, harsh radiation environment, so time is everything, and we want to get the maximum science from these systems. So this is an example where autonomy allows us to do more science in the time available before these systems end their lives, or lives are ended, I should say. One other example that I wanted to touch on, because I've been harping mostly on civil space, is a national security example. Now, in national security space, we're talking about a very large number of spacecraft around the Earth operating in constellations. And, you see these constellations, SpaceX is putting up their own constellation for internet capability. Planet Labs is doing Earth observing from constellations of spacecraft. Well, for national security reasons, constellations provide continuous coverage, they provide resiliency, the various paths to send data down around the world. And so constellations of small spacecraft, I believe, are the future of national security space. Now here, I think autonomy will be very important because we need multiple ways to send down data. You could imagine this is an example where there'll be large amounts of data, and do the operators on the Earth really need to process all of that information, or can some of that be processed on board and higher level data products provided to those operators for decision making? I'm not talking here about something as futuristic as Skynet, but I do think that this is where we're headed in national security space. And I think you'll see more and more interest and breakthroughs in these areas over the next decade. Now, the last example I want to give you is an example where autonomy is absolutely required because we're going to be traveling so far that humans can't interact with our robotic emissary in a reasonable way. And that's a mission that's under study right now at APL called Interstellar Probe. And it's a probe that's going to go out of our solar system and travel and explore in what's called the interstellar medium, the medium between our solar system and the next closest star. Right? Eventually, Interstellar Probe will get to another star system, but that'll be thousands of years. So in the life of this system, which, by the way, is going to be like 50 years, very long for a space system, it'll fly through our solar system and it will investigate the interstellar medium that we know almost nothing about today. It'll look back on our own solar system and see the heliosphere. That's the boundary of our solar system created by the solar wind and the interaction with galactic cosmic radiation. It's a shield, basically, that keeps us all safe. We'll be able to see that heliosphere from the outside looking in and understand how it varies in time and in space. So this is a mission like Voyager that are out beyond the solar system now, and New Horizons that will soon depart our solar system, where the long round trip times and the very small pipe that we have to send data back absolutely requires autonomy. There'll be segments, perhaps months, maybe even years, where we don't have contact with this spacecraft, and yet it has to stay healthy, operational, it has to be acquiring data during the entire time. The avionics are going to have to be designed for rapid recovery from faults should they occur autonomously. We don't have enough power to send all that data back, right? And so this is a mission where for most of its life, the operators on Earth will largely be watching. And then there'll be like a 2-week period where there's a lot of data that comes back and people will get excited, and then they'll go back into hibernation mode. Just to give you a sense for what I'm talking about, this spacecraft will travel faster than any human-made object to date. It'll get all the way out to Jupiter. This is something that typically takes about 5 years. It'll get all the way out to Jupiter in 9 months. All right, that's how fast it's going. After 15 years, it'll only be at about 100 AU. An AU is the distance from the sun to the Earth, so it'll only be about 100 times that distance after 15 years. And from that distance, when it sends a signal to the Earth, it'll take 12 hours for it to get here. So imagine we send a command and we tell it to verify that the command was received, send us back a signal that it was received. That's a day, right, from that distance. After 50 years, it'll be out at a remarkable distance of 375 AU, which, by the way, is still 1/1000th of the way to the closest star. So it'll be in the interstellar medium for sure. And at that point, a radio signal will take 52 hours one way to reach home. So this is why, just think about that for a moment, and that, gets you to sink in why autonomy will be needed on this spacecraft. Okay. So I've got a quick video there, and then I'll take some questions. Yeah, this is a mission, by the way, that combines the best of people, in the ideation stage with autonomy. So anyway, I could show you more. It's very interstellar-esque, as it should be. But it gives you a sense of really how far we're talking about going and the true exploration of it all. But with that, I think I'll pause and see if you have any questions. Thank you very much. Reliability.
And when you do simulation or actual experimentation, how do you define that? And I see the reliability also directly linked with the security. You have to make sure the system is secure enough, not compromised. Even the communication that's happening, that might be compromised or maybe some kind of man-in-the-middle attack. Do you take those into consideration?
Yes, so the question is about reliability and security in space systems, and we absolutely take that into account. From a reliability standpoint, we work very hard in the development of any spacecraft, whether it's automated or autonomous, right? In terms of analysis, ground-based testing, hardware-in-the-loop testing, and in some cases, if we're talking about like entry, descent, and landing, for instance, even flight testing, to prove the reliability of all the components. The challenge in spaceflight is you can't really prove the reliability of the integrated system in many of these cases. If you're landing on Mars, for example, or if you're going to be the first time that humanity impacts an asteroid that we can't even see, there is no test as you fly test bed that you can get into and do that. But what we do is we build up to that through subsystem testing, and we weave it all together through simulation. And so we do millions of Monte Carlo type runs to get at the reliability of these aspects and to define the tails of the distributions and what criteria and what components are most susceptible to problems, and then we attack those. In terms of security, yes, very much we're focused on security. And in the lead up to DART, we had quite a bit of energy and exercises devoted to making sure that our systems and our systems that connect to NASA's systems and go up through the Deep Space Network and the commanding, that all of that was secure. We even tried to spoof the systems in a number of ways, right? So that's definitely a part of what we do.
Thank you.
Sure. Yes, sir. Something about the drone? What about I got you. Yeah, thank you. So I guess we don't, but it turns out that flying on Titan is not that hard, right? Which is one of the reasons why we can have a car-sized drone that's only nuclear powered. When I say nuclear powered, by the way, it's an RTG, so it operates by radioisotope decay, and it produces only a little more than 100 watts for the entire operation. So Titan's atmosphere is very thick, unlike, so Mars is super thin, then you have the Earth, and then you have, places like Venus and Titan that have thick atmospheres. And so it's relatively easy to fly on Titan. The challenge is not density for flight, the challenge is temperature. Super cold, extremely cold. And so while there are, for example, rivers on Titan, they're rivers that have been carved out by methane and liquid ethane, because that's how cold it is. And so the challenge that we have for Dragonfly is also a reliability challenge, and it's a reliability challenge related to operating autonomously in that extremely cold environment. Okay? Thank you. Yes, sir.
Hi, I'm Matty Gall. I'm a PhD student here. Our group is presenting a little bit later. I
Awesome.
just have a question about how you guys look at edge cases. Sometimes it's kind of like it's like one way I look at it is degrees of freedom and like combinatorics of like what could go
Yeah.
on. And that's really just kind of the sky's the limit in terms of imagination. But reliability, if you can't imagine it, how do you then design for it?
Yeah, no, that's a great question. Excellent. So to be honest with you, it depends on the spacecraft. So we classify our spacecraft as Class A, Class B, Class C, Class D. A Class D spacecraft is typically like a small sat, and the kind of thing that you might develop at a university here or another university. Class A is like a flagship, multi-billion-dollar. It could have humans on board, or it could be a one-of-a-kind asset that you definitely don't want to take much risk with. Okay, and so the number of, from a reliability sense, the number of nines that we go after is very much dependent on whether it's a Class D spacecraft or a Class A spacecraft. Now, for Class A spacecraft, we look at every edge case that one can conceive. And during the initial stages of the verification and validation program, what we basically do is we get hundreds of engineers together, and they do like nightmare brainstorming, where they like try to top each other on who has the worst nightmare of how the mission is going to end. And then we, list all those out. We break them up into, we do fishbone analyses, and we break them up into constituent failure modes and effect analyses that go into reliability analyses. And then we attack each element of that fishbone with a mitigation plan, and we try to, either eliminate that risk or mitigate it as best we can. In the end, on any space mission, there are going to be a bunch of risks that you just can't address. And so our process requires us to get waivers for all of the remaining risks at the time of launch. And depending on the waiver, somebody, for instance, like at Ralph's level, or somebody at NASA, if it's a NASA mission, has to sign off on, they acknowledge that this risk exists, okay, before we even launch. For a Class D mission, that doesn't happen because it's a very different kind of spacecraft. Okay, yeah. Sure, last one maybe?
From IAA.
Yeah.
Could you please, two kind of related questions. Could you talk about some of the realistic ways that you see your organization and the academic parts of the university to collaborate? And today you talked about mission-driven activities. Are there other projects, other kinds of projects in your organization that aren't specifically mission-driven? So how do you
Yeah.
categorize your organization in collaboration?
Yeah, that's a great question, and I'm glad you asked that because I was heading that way in this talk. So I think of it's a dangerous question, by the way, for me to address in front of my boss here, but I think of APL as the applied research division of Johns Hopkins, right? And so I think that we are part of the Hopkins ecosystem. Much like, when I was at CU Boulder, there was an organization called LASP, the Laboratory for Atmospheric and Space Physics, and they were a professional research organization that did applied research, whereas on the academic side, we did more basic research. Or at Caltech, there was a similar relationship with JPL, right? And so that's the environment that I come from. That's the environment that I know and love. So that's the environment that I'm hoping to help grow. I think here at Hopkins, it's collaboration is fairly strong already. I would just like to help make it stronger. And so where I can play a role there is, in my role as head of the space sector. I don't think the space sector is as connected to the Homewood campus as we could be. I've been talking with Chuck Bennett about that, by the way. I think we could be doing much more in terms of student opportunities, in terms of staff from APL, interacting on campus, maybe teaching or other opportunities, interacting with students here on campus. I would like to do so as well. I did focus on missions because I wanted to give you some examples for how autonomous systems are starting to make a dent in a difficult enterprise of spaceflight. But in terms of research activities, we have a pretty significant IRAD program across the lab and in the space sector. And within the space sector, we're also working on a vision right now where we're going to be identifying 4 or 5 technology areas where we're going to make big bets and where we're going to invest our own time and our own resources because they're important to the sector for our applications going forward. But in terms of the investments, they're going to be more basic research investments. And then the last point I should make is, I've been up here talking about space this whole time, but APL, is a remarkable engine for innovation in robotics, autonomy, cyber, quantum, and the list goes on. The Research and Exploratory Development Department, which is right next door to me on the APL campus, some of the researchers there are just phenomenal, and the lab space that we have is outstanding. And so, I'd encourage you to talk to, Jim Schatz, who leads RED, or others in that group as well. Some of the advanced manufacturing capabilities, for instance, at APL are just, top notch. Did I answer your question? Yeah. Okay. All right. Well, hey, thank you very much for the invitation. It's great to be here. Thanks, Jim.
Wow, that was awesome. I think we're going to give you a few minutes here. What do you think, Kara? 5, 10? We'll give you 10 minutes, and we will reconvene here and begin the seed presentations led by David somewhere David Silverberg somewhere in the room. So take your 10-minute break, come back, and we'll get a chance to talk about where we're coming from, and then we'll finish that with a bit of a discussion of where we're going to. And one of the things that we want to do in IAA is invest in these relationships. So we have some additional seed funding projects, and we'd like to actually use it to help you all find ways to work with APL, including with the space folks, and envision some really fabulous projects. So thank you. 10 minutes and back in the room.